before going straight into Newton's third law, let's understand how two systems interact.
Okay, go.
This is hammer. This is nail. Boom, 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 boom.
So that hammer exerts force on the nail, so the nail pushes forward.
Ready?
If you think about it, if object A push or pull on object B push and pull with the same force back to object A.
Okay, ready?
As you can see, Ki-young pushed on Youngju and Youngju pushed back on Ki-young.
Yeah!
As Jing sits on the chair, he pushes forward on the chair. At the same time, the chair pushes upward on his ass.
Go.
This is called interaction. Interaction is two systems influencing each other.
To be more specific, if object A exerts a force on object B is going to exert force on object A with same force.
Now we can define Newton's first law. For every force action, there's an equal but opposite force reaction.
Newton's third law is easy to understand but very hard to grasp it completely. For example, consider what happens when the ball drops from the sky. If the ball and the earth exert equal and opposite force on each other, why is it that only ball drops to the ground and earth is not pulled up toward the ball? What the freak?
Go. Go.
Let's look at how gravitational force works on Newton's third law.
I'm Earth.
I'm Moon.
We're pulling on each other.
The moon pulls on the earth in response to the earth's gravity pulling on the moon. The ocean tides are an indication of the long-range gravitational interaction of the earth and the moon.
This is because the forces are equal but accelerations are not. The acceleration continues to depend on the mass, as Newton's second law states, m equals ma. In an interaction between two objects of different mass, the lighter mass will do natural of all the accelerating even though the force exerted on two objects are equal.
In conclusion, Newton's third law is great. He has three laws. The first law, the second law, the third law. First and second laws, F equals ma. Third law is the best because there's normal force everywhere. Everyone's like, oh, there's a force applied to me also.
Okay, so we're gonna do a problem, and then I'm gonna draw a picture. So, there's a rope, and there's a rope one going this way. Two, and there's a rope three. Well, let's make this rope 2 and this rope 3. Okay. Right. So this is an angle which we're gonna find, and this is 90 degrees. That's given. And me, Youngju, is holding onto this rope 2. I'm gonna call myself Climber, not Youngju or Jason. Okay, I am 90 kilograms, I think. No, I'm not, but just saying I'm 90 kilograms. And the rope can hold 1500 newtons in total. And then we're gonna find the minimum angle this can be in order for to hold you together, like put you in a rest and not break up. Okay, so given those information, we're gonna draw free body diagram. So for Yongju, for the knot, there's y direction and x direction. Okay, there's a tension going this way, which is going to be T1. And then tension going down, which is going to be T2, which is also going to, I'm going to call it T Yongju on the knot. Right? And there's, of course, T3, which is this. There's T1, T2, and T3. That's for the knot, which is here. And they're going to be free diagram for Yongju or Jason. Okay, force. There are going to be two force. Force going down and force going up. It's going to be F of G, which I'm going to also call T of knot on Yongju. And this is going to, no, actually, this is going to be here. I messed up. So T of knot on Yongju is here, and then that's F of G, which is equal to mg. Alright. Okay. I messed up a little bit, but that should be here. Alright. So, if we apply this to Newton's third law, we can say that Ty on k is equal to Tk on y. Sorry, someone called. Anyways, this is because if there's a force, me pulling down this way, because I'm at rest, there should be force that's going up. And then, since I'm at rest, those forces have to be the same. Which Newton's third law states that force, if there's one force going down, there has to be force going up as well. Like equal and opposite force. So, T of y on the k has to equal Tk on y, which is going to equal mg, because Tk on y is equal to mg. That's because on Yongju, total force on y direction is going to be Tk on y minus mg, which is f of g. It's going to equal ma. That ma is going to be 0 because I'm not moving. So Tk on y minus mg is going to equal to 0. So Tk on y is equal to mg. For the knot, total force of force on knot, x direction is going to be T3, which is this force, minus T1 cosine theta, which is this force going this way. Because one force is going this way, another force is going the other direction, we subtract, because this is going to the right, that's going to the left, which is going to be ma. This is also going to be 0 because once again it's not moving. Okay, total force on k, which is not of the y, is going to be T1 sine theta, which is going to be this direction. So for force going this direction, that minus Tc on k, which is going to be this, which is ma. This is going to be mg, because they are equal to each other. And then applying to this, they should be mg. Anyways, T1 sine theta minus mg is equal to ma, which is going to be 0. Alright. So we're gonna put all this together, I think. T1 sine theta is going to be T3 because of this. Then T1 sine theta is going to be mg because of this. And that's going to be over here. So if we do T1 sine theta over T1 cosine theta, it's going to be 10 theta, which is going to equal mg T3. Okay, so if I solve this, it's going to be theta of minimum. Theta of minimum is going to be tangent -1 mg over T3. If I plug all the numbers in, which I have here, it's going to be 10⁻⁴ mass, which is 90 kilogram, times gravity, which is going to be 9.8 meter per second square, over the tension, which is going to be 150 newtons. It's going to be maximum, which is 1. Alright, if I plug this into the calculator, I will get about 30 degrees angle. So this angle is going to be 30 degrees. You solve all this by using Newton's third law.